session is chaired by me. I'm Professor Matti Mäntäsalä from Tampere University, and then Professor Luca Catarinucci from University of Salento. So we are chairing the session, and the first title today is Hybrid Printed Electronics to Fight Pandemics, which will be given by Dr. Ashok Sridhar. And Ashok is currently responsible for the global business development of TNO Holst Center for wearable devices and smart sensing system portfolio. He has a deep technical expertise as well as strategic and business development expertise in additive manufacturing technologies in the field of printed electronics, 3D printing as an enabler for IoT and Industry 4.0. So Ashok, please be free to start your session, a presentation.
Thanks a lot, Matti and Luca, of course. Let me share my screen quickly. Hopefully you will see that without any hassles, any issues. Do you see my presentation?
Yes, now it's in a full screen mode, so please start when you are ready.
Excellent. I'll start now. Hello, everyone. As Matti mentioned, my name is Ashok Sridhar. I'm responsible for business development for healthcare and wearables portfolio of TNO Holst Center. In the next few slides, I'll explain the background of Holst Center briefly. So the topic of my presentation today is hybrid printed electronics to fight pandemics. So let me first introduce you to the content of my talk. First, I'll briefly introduce myself, although Matti already introduced a bit, so I can skip that part, I think. But I'll introduce our R&D Innovation Center, Holst Center, located in the Netherlands. Before moving on to the core of this presentation, first by giving the background to the COVID-19 pandemic, and then highlighting the need for seamlessly integrated electronics, before moving on to the technical core of this presentation, which is hybrid printed electronics. So how hybrid printed electronics can enable seamlessly integrated electronics, which in turn help us fight and manage such situations as COVID-19. And I'll conclude my talk with some takeaways. First, an introduction to myself, briefly. Ashok Sridhar, as I mentioned, I have a mixed techno-commercial background, a PhD in printed electronics from the University of Twente in the Netherlands, and an executive MBA from the TIAS School for Business and Society, also in Netherlands. Over the past roughly 15 years, I've held many techno-commercial roles in printed electronics, but also in 3D printing. About Holst Center, Holst Center is an R&D innovation center founded in 2005 by the Netherlands Organization for Applied Scientific Research, which is abbreviated as TNO, and IMEC, which is the Belgian Microelectronics Center, each of whom have 3,000 to 4,000 employees roughly. Holst Center itself has 200 employees approximately, mostly scientists and engineers. We are located at the high-tech campus in Eindhoven, which is by some measures the smartest square kilometer in Europe in terms of, let's say, scientific and technical output. What we do at Holst Center is we enable electronic devices that are flexible, stretchable, wearable, washable, even 3D formable. So all kinds of form factors for next generation electronics. We focus on mainly on healthcare and vitality domains, but also on mobility, especially automotive, Internet of Things, and energy. And for energy, we have a spin-off for printed batteries, for example. We are not a commercial company in the sense that we bring products to the market, but we help other companies from around the world, right from Canada, US to Japan, and almost every country in between. We help companies to bring out products with seamlessly integrated electronics for these domains. So since this presentation is about healthcare innovations, I'll give you a brief snapshot of our innovations over the past decade in healthcare. I'm not going to go too much into details, but just to give you a snapshot, right from 2010, even earlier than 2010, we worked on a jaundice blanket. It's a blanket with integrated blue light LEDs. With UV light, you can actually break down bilirubin, which actually causes jaundice. So this blanket is meant for infants to break down bilirubin and minimize the effect of jaundice. Sorry. And over the years, then we developed innovations such as wearable health patch for monitoring vital signs, which I will show in one of the slides, some of the slides. Then flexible images and detectors, baby monitoring belt to monitor premature babies if they are taken out of incubators. Then focusing on large area distributed electronics to come up with innovations such as large area sensing mats that can be integrated in mattresses, for example, to monitor elderly people or infants. And we are also working on textile integrated intelligence sensors for stress minimization, for example, but also for measuring vital signs. So this is a snapshot of our innovations over the past 10 years in the healthcare domain, product innovations that is. So the background to this, or for this presentation, is the current COVID-19 pandemic scenario. I mean, I don't have to tell you, we are all going through the suffering through this, of course, and hopefully the light is, we can actually see the light at the end of the tunnel, which is a good thing. But over the past 2 years, we saw that in several countries, including developed economies, the medical infrastructure could not cope up with the surge in demand. We could see patients had to wait for days to get treated, sometimes in the corridors of the hospital, even people passing away in the corridors of hospitals, outside of hospitals, heartbreaking scenario. But the healthcare professionals, doctors, nurses, and frontline care workers, they were the ones that actually bore the brunt, actually still bearing the brunt of COVID's impact. Excuse me. So yeah, I mean, they had to work extremely long hours, multiple shifts, a couple of shifts per day, and over a sustained period of time, it also took a toll on them, literally. So this crisis, this healthcare crisis, has highlighted the shortcomings in the way healthcare is currently being delivered. It doesn't have to be this way. So decentralizing the healthcare system, or decentralizing healthcare delivery using digital health technologies, is the way forward to ensure human centricity. So placing people first, or people at the center, and then delivering healthcare to them in a preventive, in a proactive way, is a way forward, and not just treating them at the hospitals after something has happened. Of course, it will happen. Treatment at the hospital is never going to go away, but can we monitor, let's say, people who are the high risk group or who are infected already at their home settings in a proactive manner, and at the right time give the right care to them. So this approach results in better medical outcomes, improved patient experience, lesser load on medical professionals, and the overall affordability of healthcare. A couple of pictures, again, quite sad pictures actually, one from New York Times, another from the Telegraph, showing how much on the left-hand side the healthcare workers have to go through, and still having to go through in countries like India, for example, in Brazil and so on. It still continues to this day, the scenario. And on the right side, you see the ambulances waiting in a row, in a queue, to enable the patients in the ambulance to get to the hospital. So there is a queue for everything, even in developed countries at certain point during this pandemic. Again, it doesn't have to be this way. So as I mentioned, the way forward is to bring care to home as much as possible in a way that it's compatible and complementary to care at hospital. So today, the wired solutions in clinical settings is the main way of monitoring a person's well-being. And the future and the emerging trend is to monitor him or her in a remote setting at home even. And with the advent of more and more wearable devices, with the insurance companies being more and more receptive to these devices, and also 4G and eventually 5G implementation, will all help aid and accelerate the shift in the way healthcare is delivered. At the same time, there is a strong need for seamlessly integrated electronics. For example, if you want to measure or monitor someone at a home setting, especially if that person is not yet infected, but he or she is part of the high-risk group, you can't ask him or her to wear bulky devices that are uncomfortable. So the electronics has to basically disappear on the skin or into a textile or whatever. So there is a need for seamlessly integrated electronics for situations such as these. The current electronics, a little bit exaggerated, of course, but the current electronics is rigid and boxy, pretty thick and non-conformal, and certainly not comfortable to wear on the skin or in a textile. But if you actually look at the current PCBs, they are too restrictive for futuristic applications that I just highlighted. May it be monitoring at home or infant monitoring or textile integrated sensing and so on. They are too restrictive. Ideally, one would want this. What you see here is circuitry that is flexible, sensors that are flexible, stretchable, formable to 3D shapes, even wearable and washable. So ideally, one would want this to enable remote monitoring with seamlessly integrated devices in everyday items and also on the skin. The solution we are proposing, of course, is hybrid printed electronics. Let me explain what hybrid printed electronics means, for which I will start with the printing technologies. By making smart use of additive printing technologies, such as screen printing, inkjet printing, or gravure printing, or whatnot. So these printing processes exist for many, many years, decades, even centuries in some cases, some of them. They have been existing to print graphics, to print on paper, and so on and so forth. But these can also be used to print electronics. With the advent of new materials and inks that can be conductive, can be dielectric, semiconducting, resisting, and whatnot, it is possible to use printing technologies to print the circuitry, even complex multi-layered circuitry. And this can be done since it's additive manufacturing, it's additive printing. Unlike the traditional PCBs, which are typically etched, chemically wet etched, they have a specific substrate requirement, thicknesses and form factors and so on. Whereas here, printing enables addition of circuitry in many kinds of substrates. For example, rubbery materials such as TPU, thermoplastic polyurethane, silicons, textiles even. And for smart plastics that require 3D shapes, polycarbonate PMMA, for example. For disposable and low-cost devices and tags, papers and polyesters can be used. So horses for the course, depending on what kind of application we are talking about, one can select this right substrate material in the right thickness and form factor. So I'm going to show in the next slide a sequence of printing steps to show how we get from a plain substrate. What you see here actually is the ground plane printed using a conductive ink on a transparent substrate, which is actually, you can see that there's a character Holst center written here, our institute's name. So it's printed on a transparent polyester substrate along with this electrode, the ground electrode. That's the first layer. Then comes the second layer with some isolation in between, this whitish paste you can see. And then further addition of conductive circuitry, for example, for where the chips will be, the microcontroller will be bonded. And in this case, you can see stretchable meander patterns to enable stretchability of the circuitry. So all this is achieved, what you see on the screen is achieved in one printing step. And also the antenna here for Bluetooth up there. Then one more layer of dielectric to isolate a conducting circuitry with the next layer, and then print the next layer and so on and so forth. In this manner, we can repeat it many, many times. We have done up to 40 times even at fairly high resolution, as you can see, down to 30 micrometers line and spacing, to get to very high density complex circuitry by additive printing. But that said, that's printed electronics, of course. That said, certain functionalities like processing, wireless communication, LEDs, passives even, we need off-the-shelf traditional components. So in a judicious way, by combining the traditional electronic components with printed circuitry and printed sensors, we come up with hybrid printed electronics. So it's a hybrid of printing and traditional electronics. Again, since we mostly use low-cost materials and low temperature resistant materials for these PCB substrates, one has to innovate new processes to assemble these components onto the circuitry. For example, conductive adhesives or solders that are not reflow soldered, but instead photonically soldered. So a lot of innovations have gone into it to create this hybrid system. So that's the technical background of the presentation and the use cases I will show in the next few slides. So key advantages, again, to drive home the message, scalable in substrate size from centimeter square to meter square, large areas, compatible with large volumes. One can print in a sheet to sheet manner or in a roll to roll, high throughput manner, several meters per minute, even several tens of meters per minute can be printed. It's additively manufactured, so it's sustainable and it's green, much greener than the current wet etching processes. A broad range of materials can be used for both the inks and the substrates, as I mentioned, and of course, ultra thin and flexible and stretchable form factor. These are the key advantages of hybrid printed electronics. Now I'll go to the use case. The use case one for a pandemic scenario is health patch. So health patch is actually the patch is a device that can be used like a band-aid. It's stuck onto the body at different positions where required to monitor physiological parameters in a remote setting. So there are no wires, there are electrodes, printed electrodes in this case, and it's also a device that's encapsulated. So the person wearing it can go into the shower if need be. And this can be on the skin for several days, up to a week even, and continuously monitor or measure parameters such as ECG, bioimpedance, so from which respiration rate and respiration depth can be calculated, skin temperature, and so on and so forth. But there are more sensors that could be added, which I'll show on the next slide. And such a device that can monitor and wirelessly communicate it to a cloud, for example, that can really relieve the burden on the healthcare system and the caregiver.
很少是一个的，除非他是一个人，一群人的话，如果说旁边有。
All right, someone was talking in the background. Anyway, I'll continue. It can, as I mentioned, it can wirelessly transmit the data, and the caregivers can access it without the person or a patient having to come to the hospital unless it's absolutely necessary. One of the positive impacts, if I may say that, of COVID-19 is that it has accelerated the implementation of such monitoring devices in the healthcare system. As I said, insurance companies are more and more receptive and willing to reimburse. Actually, recently, we probably would have noticed that Philips Healthcare, which is also located in the same city we are in Eindhoven, in Netherlands, that's the headquarters, they recently acquired biotelemetry for whopping sum of, I think, $3 billion US dollars. Biotelemetry is a US-based company that actually has a platform for remote monitoring devices such as these. So one sees that it's creating a snowball effect in the positive sense. So a patch is not just a patch, it's actually a platform. At least in the way we design it, we develop it, it's a platform. So apart from the ECG and bioimpedance I mentioned, a wide range of parameters can be measured and sensors can be implemented, including temperature, accelerometer for posture, even ultrasound transducers, SpO2 for blood oxygen level, which is very important for COVID again. But also actuators such as micro pump, for instance, for diabetes or insulin injection, electrodes for stimulation, and many other possibilities to integrate advanced functionalities like dry electrodes, wireless communication, and so on and so forth. So a patch is a platform which is a fully self-sufficient device that can measure and communicate to a cloud. And this could go a long way should a scenario such as COVID-19 occur in the future as well. I hope not, but one never knows. So yeah, these things could be of great benefit in such a scenario. Last slide on the health patches. The way we approach this patch technology is that we have a disposable part. You can see this bird wings shaped structure with printed circuitry that's stretchable. These are electrodes here, or dry electrodes. We don't have to have hydrogels to bond these electrodes onto the body. That's again very skin friendly and biocompatible. And this is the reusable part, which can be used many times for over a period of a year even, because this contains an expensive readout, and it contains a Bluetooth chip and battery and so on and so forth. So this can be disposed on a daily basis if necessary. So the idea is to bring the cost down so that this disposable part becomes economical for large-scale commercial implementation. Use case 2, smart face mask. In this case, again, when the COVID pandemic struck, we actually brainstormed internally and came up with this innovation. Of course, we are not the only ones. So in a face mask, which is now very commonplace, even beyond the pandemic scenario, people will continue to wear face masks. And of course, going beyond healthcare industry, also people working in chemical industry and exposed to harmful environment will wear face masks, of course, on a daily basis. So many smart functionalities can be integrated in a face mask. And this could be a great thing, especially for caregivers and healthcare workers, because without bothering them, they have a mask anyway. And as you also saw in one of the slides before, and functionalities such as temperature sensing, humidity to know if the filter is saturated or not, or even vital signs monitoring, for example, for respiration rate and depth, because it's very close to the nose, can all be captured and wirelessly communicated, so the caregivers can be taken care of, which is also very important. And we can also add more functionalities such as anti-counterfeiting, which is very important, but also ensuring the mask is worn properly without slack, because if the mask is not tight enough, or if it's too tight, both are not recommended, obviously. So by integrating strain sensors and customizing them on a person-specific manner, this can also be taken care of. So again, we see this as a platform where different functionalities can be integrated depending on the application requirement. And of course, here the circuitry is shown on the outside just to show how it looks like. But typically, these sensors should be in contact with the skin or close to the skin on the inside. Technological building blocks of this mask, again, the circuitry, it should be flexible and stretchable for ergonomic reasons. We use screen printing of the stretchable circuitry, and also the antenna, as you might have noticed here. This, in this case, is an NFC antenna, again printed. And the components are assembled using a conductive adhesive because it's a low-cost TPU substrate or low TG TPU substrate. And the components are typically reinforced by underfill material. Then, of course, the programming of the chip, it could be NFC, it could be Bluetooth or RFID, depending on the communication distance and the protocol that's required. And then this device, this tag is laminated onto the mask. That's the easiest way to achieve smartness or smart face masks. But it is also possible to directly print circuitry on the mask. For example, for simple functionalities, as you see in this case, an antenna with a chip, for instance, to communicate whether the mask is authentic or not, or to transmit some kind of pre-programmed data. So you can see direct printing of conductive structures on a mask material. So again, this could go a long way in helping, especially healthcare workers, to monitor them proactively to ensure their well-being as well. But it's also applicable for regular people like us. And it can be fashionable too. So working with a fashion designer named Marina Tuters from Netherlands, we actually developed these face masks that are fashionable. So they do not have to be boring. And on the inside, of course, the outer shell is this customizable, fashionable clothing. On the inside, the filters can be provided with this mask. Of course, in this case, this tag is too big. It will block the pathways for air for being filtered in and out. So this can be, of course, made much more compact, and this can be replaced or reused or whatever. So all possibilities are there. My last use case, in view of time, I'm rushing a bit. Last use case is smart clothing for stress reduction. So here, this is very important because this pandemic scenario forced us all into lockdowns. Many people, elderly people, or people, even single people living alone, a risk of stress-related issues, burnouts, it's enormous. And many studies showed that in the pandemic period, the number of people affected by loneliness has dramatically increased. And of course, stress directly results in healthcare issues in the longer term as well. So how can this be mitigated or minimized? One example is integrating electronics in in clothing, and then healing by the power of touch. So one example I have shown here is, again, a fashionable piece of clothing that can be worn on a daily basis. And on the front side, which you don't see, there are sensors to measure the stress levels of a person, for example, by heart rate or respiration rate. And then on the back side, you see along the spine, there are thin vibration motors that are positioned along the spine in a specific distance and an arrangement. And these actuators can vibrate in a pre-programmed sequence and amplitude and frequency and so on and so forth to help the wearer to calm down by guided breathing. Of course, it's the power of touch. It's a snug fit clothing, so it's touching the skin. And by the sequence of vibration, it guides the wearer to breathe and calm down so that the symptoms of stress can be minimized or mitigated. So this is one such innovation that can again help people who are stressed, not just in a pandemic scenario, but also in day-to-day life. For example, while presenting like I'm doing, I can also be calmed down by a device like this. Again, so I explained all these already in the previous slide. There are a few other things that we have innovated. For example, I do not have a picture here, but we developed a smart headband integrator that is a fashionable piece of clothing for a company called Nirax based in the US. on the west coast of US. So this has an array of infrared sensors positioned in an appropriate location in arrays, and it's conformal and stretchable. So this infrared light can penetrate the skull and create an effect called photobiomodulation. Thereby, it minimizes the stress symptoms, interacts with the brain, minimizes stress symptom proactively, so that the wearer is not stressed out, and consequently, he or she can lead a more vital life. So smart clothing is also a way to have seamlessly integrated electronics to help people to live healthily. So the last slide, conclusions. The COVID-19 pandemic exposed the flaws in the way healthcare is currently delivered. Instead of treating patients after something has occurred, it is more efficient and effective to proactively ensure the well-being of human beings. Human-centric healthcare is what we call this, proactively helping people. Hybrid printed electronics offers the appropriate technological building blocks to enable seamlessly integrated electronics to monitor health and well-being of human beings. And finally, remote monitoring devices enabled by this will go a long way in helping the society to be better prepared for future pandemics. With this, I would like to thank you for your attention and thank the organizers, Matti and Luca as well, for providing me this opportunity. Thanks a lot.
Matti, switch on the microphone.
Okay, good. Thank you. So if you have any questions, please send those to chat or raise your hand. I don't see any hands at the moment, so maybe I'll start. So Ashok, you showed great applications. So in your opinion, what are the biggest obstacles in the technology at the moment?
Thanks, Matti. That's a very good question, very relevant question. The biggest obstacles, there are obstacles, obviously. So if you talk only about the technology part and not the implementation part, I would say the reliability of these devices. I mean, if in a pandemic scenario, for example, a care worker may be a doctor or a nurse or frontline care workers, one cannot instruct them to handle this device in this and this manner. I mean, they are already stressed, and these devices will be most likely mishandled, so to speak, not intentionally, but are they reliable enough to keep measuring the vital signs, especially, and communicate the right data? What will happen, for example, if the skin contact is not, the integrity of skin contact is damaged? For instance, if the contact to the skin, for instance, for measuring the temperature, if there is some kind of a sweat layer or air gap in between, how accurate are the measured values? And can one take clinical decisions based on what is measured by these devices? So these are big challenges, obviously, because having a smartwatch to monitor your heart rate and breathing rate and what are the step count or whatnot for your own information is one thing. It can be inaccurate. It doesn't have to be, but it can be inaccurate. But medical grade data that is delivered through wearable devices, that is still a challenge. So the repeatability, reproducibility, and the integrity in all kinds of circumstances is something that needs to be improved further.
So continuing for that one, actually, so how much clinical evidence you already have with these applications? Are these really coming on the market and with the FDA approval, or?
Yeah, so for Health Patch, for sure, we are already at TRL 7. Of course, we are not a commercial company, so we stop with it and we allow the others, companies, startups, big companies, we transfer the technology so that they can use the building blocks and develop their own devices. And some of the customers, I don't want to mention the names, but I did already mention one, which is Nirax, for example, in smart clothing area. But in Health Patch, I can mention, of course, it's public. Philips, for example, they have used our building blocks to have commercial devices in the market, so approved devices. For example, Philips Health Dot and Nirax Smart Headband being two examples, and a few others in the smart clothing domain. For instance, this infant monitoring belt, which is again textile integrated. This is going through clinical trials. So a number of innovations that we have helped create are either in the market or going through clinical trials. And of course, we are not the party that proactively performs clinical trials because we are not the end product manufacturer.
Thank you, Ashok. I don't see any questions in the chat. I don't see any hands raised. So let's go forward.
Thanks
Sorry?
a lot.
Yeah.
Appreciate.
So yes. So I think so. It was excellent talk, but most of the times when we focus more on applications. As you said, reliability could be a concern. See, my question was like, are we even sure about the materials which are printed? Like at least if we take for conductors. So do we have enough options for stable conductors?
Yes, that's a very good question.
Or,
So
for matter any other material, yeah.
That's a very good question. So this is why an ecosystem is very important. So it is not a one company game. It's not a one research institute or university game. It is actually an ecosystem. So of course, Matti here knows all about it. But speaking for Holst Center here, over the past 15 years, we have built an ecosystem of suppliers. I can mention some names like DuPont, Shin-Etsu, Henkel, and so on and so forth, that manufacture these materials. And it's not like they manufacture and then push these. They proactively work with us and also probably with other research institutes to optimize their materials in an application-specific manner. So in this manner, for example, conductive materials, there are so many of them these days that are actually implemented in practical applications. May not be just be for healthcare, but also an automotive application, but also an IoT. So the answer to your question is by proactive R&D, also from the material supplier side, these issues have been addressed and also are being addressed. So yes, there are materials that are integral enough to fulfill these functionalities, but it's a question of the whole system. Can the system integrated in a textile or in a chair or in a mattress and whatnot, can it perform the way it's intended to, given all the boundary conditions it's exposed to? That's more the challenge and not the material itself, I would say, in my opinion.
Thank you so much. Thank you.
Sure.
Thank you.
Thank you.